Neutron star comes to Earth. Welcome, friends, to, or maybe it's the cough syrup, the show where we strip down the smoke and mirrors of digital fear, uncover a few clever tech tricks, and yes, laugh at the occasional human stumble. I'm your host, Brock Chestnut. Maybe you caught me in such classics as Do Not Click, Fishing Activity Trends, What's New in Fishing, or the cult favorite romance novel Injuries. Today, we're diving into a neutron star visiting our solar system. And remember, this ride is strictly for entertainment. No guarantees, no warranties, no promises, except a good time. When a neutron star visits our solar system, this is a speculative scenario. It is built on scientific principles taken from research on neutron stars, particularly their tidal effects, magnetic fields, and compactness. But it also stretches imagination, following what might happen if such an object wandered into our solar system and eventually intersected with Earth. Opening, imagine an ordinary night sky, quiet, unremarkable. Hidden in that darkness, a tiny object approaches, a sphere only about 20 kilometers across, but weighing more than our sun. It is a neutron star, a stellar remnant so compact that a teaspoon of its matter outweighs Mount Everest. What would happen if such an object passed into our solar system? How would we know? What clues would appear first? And what would unfold as it drew closer, eventually intersecting with the Earth itself? The first signs. Our first detection would almost certainly come years, even centuries in advance, through its gravity. Astronomers surveying the sky would notice subtle micro-lensing events. Background stars would brighten for days or weeks as the neutron star's mass bent their light. Telescopes like Gaia or future astrometric missions would record tiny shifts in stellar positions, betraying the presence of a massive but nearly invisible object. If the neutron star happened to be a magnetar, with magnetic fields trillions of times stronger than Earth's, we might also pick up unusual bursts of X-rays or gamma rays detectable by space telescopes. In that case, we might know even before gravitational clues appeared. Charting the path. Once noticed, scientists would combine astrometry, gravitational lensing data, and orbital perturbations of distant solar system bodies to reconstruct the intruder's trajectory. Computers would model a hyperbolic path through the solar system, updating forecasts with every new observation. The mass would be inferred from lensing curves. Its compactness, how small and dense it is, would match neutron star equations of state. The verdict would come quickly. This is no asteroid or rogue planet. This is a collapsed star, inbound, drawing near. At first, little would change. A neutron star is so small that its visible light output may be dim. Unless it is still young and hot, glowing faintly in X-rays, it would remain an invisible bullet in space. But as it crosses the outer solar system, gravitational signatures mount. The orbits of Kuiper Belt objects shift, comets are perturbed, planetary ephemerides no longer fit predictions. By the time it crosses Jupiter's orbit, its gravitational tug becomes undeniable. Entire planetary configurations shift by tiny but measurable amounts. Crossing the Moon's orbit, now imagine the neutron star only 384,000 kilometers away, the distance from Earth to the Moon. At this proximity, the consequences are catastrophic. Tidal forces scale with the star's mass and the cube of its distance. A 1.4 solar mass neutron star at lunar distance would produce tides tens of millions of times stronger than the Moon's. The Earth's crust would shatter. Oceans would rise thousands of meters in moments, then rip away entirely. The atmosphere would shear off into space. The very mantle would spall and tear. Earth becomes a stretched droplet of molten rock, unraveling under forces it cannot resist. The Moon itself would be ejected or shredded, its orbit destabilized instantly. Magnetic catastrophes. If the neutron star were a magnetar, an additional dimension of destruction unfolds. At close distances, its magnetic field induces currents in Earth's core, atmosphere, and even in human-made infrastructure. Power grids fry instantly. Electronics vaporize in arcs of current. Radiation belts realign, bombarding what remains of Earth's surface with deadly particle storms. But gravity has already doomed us. The magnetic show is merely an encore. The impact on Chattanooga. Let's push the thought experiment further. Suppose, impossibly, that the neutron star continues inward as if to strike Tennessee. Here's the truth. The Earth would not survive intact long enough for an impact. Long before the neutron star reached the ground, our planet would have been pulverized into a debris stream, orbiting or spiraling into the compact star. Still, let us imagine, the neutron star descends toward Chattanooga, a city nestled along the Tennessee River. Instead of a fiery asteroid impact, there is silence. The object's immense gravity pulls not only the city but the entire continental crust into an elongated ribbon of plasma. There is no explosion in the cinematic sense. Instead, matter is stripped away, atom by atom, compressed into accretion flows around the star. The neutron star does not so much hit Chattanooga as absorb it, along with the rest of the Earth. The broader perspective. This scenario is almost inconceivably unlikely. Neutron stars are rare. Only a few 100,000 exist in the Milky Way. The galaxy is vast. The odds of one passing through our solar system in any human timescale are effectively zero. But as a thought experiment, it illustrates several key truths. Gravity reveals all. We would first detect such an object not by sight, but by its gravitational fingerprints. Tides are lethal. Long before any surface encounter, Earth would be torn apart by tidal forces. Magnetism adds flavor. Magnetars could broadcast their presence through radiation and electromagnetic devastation. No survival. There is no mitigation, no planetary defense. Against a neutron star, our solar system itself bends in surrender. Closing reflection. Neutron stars are both terrifying and awe-inspiring. They remind us of the power locked inside collapsed matter, of how fragile our planet is, and how vast and unpredictable the cosmos remains. If one were to wander into our neighborhood, our fate would be sealed. But in studying them from afar, through gravitational waves, pulsar timing, and X-ray bursts, we learn not just about death and destruction, but about the fundamental nature of matter itself. And so, while Chattanooga and the Earth are safe, the thought experiment is worth the telling. It is a humbling reminder that in the theater of the universe, we are small players beneath forces we barely understand. All right, my friends, that's a wrap for today's ride. You've been keeping company with me, Brock Chestnut, former romance novel cover model, now curator of fine wines and cigars for the world's most particular palates. I like to think of this little corner of the airwaves as a humidor for ideas, some bold, some smooth, all worth savoring. If today gave you a spark, go ahead and subscribe. Share it with someone who knows the value of a good story, or at least a good laugh. And if you're feeling generous, leave a review so more curious souls can stumble into our circle. Until next time, keep your glass full, keep your questions wild, and never forget, life is best lived with a little smoke, a little mystery, and stories just a touch larger than life. This is Brock Chestnut, signing off.